Okay, today we're introducing some logarithms and how we manage to evaluate logs. Okay, so what you need to know is that logarithms are the inverses of exponentials. Okay, exponential is a one-to-one function, right? So that means it has an inverse. An exponential has an inverse. We call the inverse of an exponential graph a logarithm graph. Okay, so because of that fact, there are some interesting ideas here. So we say that the log has a base of a, right? Log base a that corresponds to the similar base in its corresponding exponential. Okay, so this is how they are related. Now, in my classroom, I have this poster on the wall to remind everybody about how we do this exponential to logarithm rearrangement. Okay, so basically, this is what it looks like. So this is our exponential form. We have some base, which is usually a number, raised to an exponent. The exponent is usually the power, right? I mean the variable. So like 3 to the x. 3 to the x equals 9, or something like that. Okay, so this is our exponential form. Now we take this exponential form and we rearrange the furniture in order to make it into a logarithm form. So the first thing we do is we add the word log. Okay, you can't have a logarithm without the word log. So we write down log. Okay, the base from your exponential becomes the base of your log. The base of your exponential becomes the base of your log. Okay, the number in your exponential becomes the argument of your log. Okay, so that part goes there. And then we have the equal sign, because all equations need the equal sign. And then your exponent comes over here. Okay, that's really important to understand that this is the exponent. Okay, so this is how we're going to rearrange our furniture to answer all of these log questions. Okay, because the answer to a logarithm question is an exponential. Okay, let me write that down. The answer to a log is an exponent, right? Because logs and exponentials are inverses of each other. So of course, one would be used to answer the other, right? Just like squaring and square rooting. Those are inverse operations, multiplication and division, right? Addition and subtracting. Well, logging, and exponentiating are inverses of each other. So let's take a look at how this happens, right? Let's look at some of these. So first we start off with some logs, right? So this is log base 2. And the first thing we're going to do is replace x with 32. Okay, so we are trying to evaluate log base 2 of 32 equals what? Right, what does that equal? So we answer this question by first rearranging our furniture. Okay, so here is your base 2, here is your triangle, 2 to the what power equals, here is your blob, 32, right? So we're given a logarithm and we're rewriting it as an exponential in order to answer our question, right? Because I just got done saying the answer to a logarithm is an exponent. So I have to somehow create an equation that has an exponent in it. So I rewrite my logarithm as an exponent, right? So our base is 2. Your exponent is the question mark, or the answer. The answer to a log is an exponent, and 32. So now our brains need to think, okay, 2 raised to what power equals 32? How many times do I multiply 2 by itself in order to get to 32? And the answer is 5 times. Okay, so if I take my 32 and I rewrite it as having the same base as what I'm looking for, right? 32 is AKA 2 to the 5th. So then my answer is going to be the exponent. The answer is 5. Okay, so I can come back here to my problem, and I can erase my question mark, and I can write in the actual answer of 5. Log base 2 of 32 equals 5 because 2 to the 5th power equals 32. Okay, now this is a totally different way of thinking than any other math topic is these logarithms. So let's practice our thinking. Okay, log base 3 of 1 equals what? Right, that's how we first start off this question, by saying log base 3 of 1 equals what? And we answer that question by rearranging our log into an exponential. So we're asking ourselves 3 raised to the what power equals 1. 3 raised to the what power equals 1. Okay, so this is actually an identity that we should just memorize. Anytime we're trying to raise something to a power, let it equal 1, that power is 0. Right? Anything to the 0 is 1. 5 to the 0, 9 to the 0, 1/2 to the 0. So our answer, anytime we have 1 as the number in your argument for your log, the answer is always going to be 0. Okay, let's continue on here with this wonderful logarithm stuff. Okay, now we're going to replace x with 4. So we're trying to evaluate log base 2 of 4. Equals what? What does that equal? Well, let's change it into an exponential. 2, right? 2 is your base. 2 to the what power equals 4. 2 to the what power equals 4. And hopefully you know that 2 squared equals 4. So my answer is 2. Right? And that's pretty simplistic, but I would change my 4 into a 2 to the 2nd power, right? Because I want my bases to be the same. Because when your bases are the same, the exponents have to be equal. So the answer is 2. Okay, oh, this one looks even trickier. And it is. This one definitely is trickier. Okay, we have to remember more things when we're doing this type of a problem. So notice we have a fraction here. Okay, so the answer that we get will apply to basically all of the fractions that we're going to do. Okay, so we can make a general rule out of this one once we discover what it is. But first we go back to our standard thought process and do 10 to the what power. Remember, 10 is your base. 10 to the what power equals 1 over 100. Okay, 10 to the what power equals 1 over 100. So one of our strategies is, can I write 100 as 10 to some power? Right? 100 is 10 to the what power? Exactly, 10 squared, because 10 times 10 is 100. Okay, so now I'm pretty close, right? This side is a numerator, and this one is a denominator. But I can apply one of my exponent rules in order to make this no longer into a fraction. Okay, and that says that I can bring this up to the numerator by making the denominator negative. Okay, if I ever have a fraction with the power, I can make it no longer a power by making the the power negative. Okay, so now I think I can see what my answer is. Since the answer to a logarithm is an exponent, my exponent is -2. Okay, so in general, anytime we have a fraction that we're looking for, our answer is going to be a negative. Okay, we're always going to get a negative number when our, I don't know what to call this thing, our argument, when your argument is negative, when your argument is a fraction, we're always going to get a negative as the answer. Okay, and we'll see that come up here in a couple of minutes more. So let's do the same thing for all of these. We're going to write them all in a second, and then we'll talk about what to do after that. Okay, so let's rewrite these as our exponents. Okay, so we have 5 to the what power equals 25. Okay, and that is, of course, 2, because we can change 25 to be 5 squared, and your exponent is going to be 2. Okay, so this one, the answer is just 2. Now, our next one is quite tricky. 64 to the what power equals 8. Okay, now I say tricky because we haven't done a whole lot of this since Algebra 2, which has been quite a while for some of you. Okay, but what operation can I perform on 64? One single operation in order to change that into an 8. Okay, and the answer is I can take its square root. Okay, if I take the square root of 64, that gives me 8. I don't think anybody would argue with me on that. Now, 64, the square root, right? The square root is a special symbol that can be written as a fractional exponent. Okay, the square root is the 1/2 power, right? Because it's the square root or the second root. So when we take our fraction, oh, I just said it. The answer is a fraction. Okay, so when we're taking a root, anytime we are simplifying by rooting, right, taking a square root or a third root, we're going to get a fraction as your answer. So this is going to be the 1/2 power. It will always be a fraction. It will not always be 1/2. It's only 1/2 when you take a square root. So this next one is 125 to the what power equals 5. Okay, so we can do one operation here, and that is taking the third root. Okay, the third root of 125 equals 5 because 5 cubed equals 125. Okay, so we take the third root, which means this is 125 to the 1/3 power. Okay, so our answer for this one is going to be 1/3. So anytime we have a larger base, notice this base is 125 and your number is 5. Anytime your base is larger, we're going to have a fraction for the answer. Okay, but what about with the craziness like over here on our last example, letter H? 8 to the what power equals 32. Okay, now notice 8 and 32 really don't have any powers, right, to itself. 8 squared is 64. 8 to the first power is 8, so it's going to be somewhere between 1 and 2, but let's figure it out. So what we want to do is think, can I write 2 and 32 with a common base? Right? Can I make these into a base raised to some power? So you really need to know your problems. So here, 8. 8 is also known as 2 to the 3rd power. Right? 2 times 2 times 2, that is in fact 8. So 32, as we discovered up above in the first problem, is 2 to the 5th power. Right, so if we can express our two numbers with the same bases, right, if they have the same bases, then that means the exponents must be equal. Okay, if the bases are the same, then the exponents have to be equal. So 3 times some number equals 5. So dividing both sides by 3, and that number happens to be 5/3. Okay, so yes, this is tricky. Nobody thinks like this on a regular basis, which is why these are kind of hard, because your brain hasn't been trained to think like this. Okay, but it's good thinking, right? Good thinking. So now let's look at our properties. Here are your properties. Okay, I had these as a poster on the wall. These are 4 of our log properties. This one is called the inverse property. Right, when your bases are the same, they cancel each other out. So we have a base of A and a base of A. Right, we're going to see that come up a lot. And this is our 1-to-1 property, that these two parts need to be equal. Okay, so let's look here. if we have log base 2 of x equals log base 2 of 3, then what has to be true about these two numbers? They have to be the exact same. Okay, so in order for these to be equal, my x value has to be 3. Right? They have to match up if they're going to be equal. Okay. Number, whatever this is, log base 4 of 4. Okay, so I can rewrite this as my exponential. 4 to the x power equals 4. Okay, so we need to think, what is the power here? What is the power on every number if we don't see a power? Well, it's just 1. So here, x equals 1. Okay, so this is one of our properties. When the bases and the numbers are the same, the answer is your exponent. So there's a 1, right? If you don't see a power, we can assume that the power is always going to be a 1. So we're going to apply that same thing right here. Notice log base 5 of 5. What things are the same? The bases. The base of 5 and the base of 5 are the same. So in essence, these undo each other, and the answer is your exponent. So this is just x. Whatever the exponent happens to be is the answer to your problem. Okay, same thing here. Here we have a base of 7 and a base of 7, right? So these all cancel each other out, and the answer is 14. Okay, when everything cancels, the answer is your exponent, so 14. Okay, now natural log. Natural log is a tricky little bugger, okay, because natural log is really log base e. Okay, so e is what's called the natural number. It's 2.71828, repeating. Okay, so log base e is actually a number, right? It's not log to a variable. E is a number. So notice what we have. Log base e, we have the same bases. So all that stuff cancels out, and your answer is just 6. Okay, so natural log and e, those are the same bases. Right, e is a number, natural log is log base e. So same thing here, this is log base e, so the e's cancel out, and your answer is just 7. Okay, we'll do a lot more of these in the future where we're just trying to simplify your equation. Okay, so those are some log basics. I hope you feel better about logarithms and rearranging the furniture from a log to an exponent.